So Jonathan is a senior hydrologist with an interest in all aspects of the global water cycle, but is currently focused on computational modeling of surface water dynamics. He received his BS from California State University, MS from University of California, Irvine, PhD from University of Alabama, where he researched physics-informed machine learning techniques for operational flood forecasting. So today he will be leading the discussion on opening the black box of deep neural network via information by Schwartz and Tishbai. Yeah.
Yeah, cool. All right. So we do have some people trickling in still, but it'll be good to start. So I'll share my screen. Real quick, let me find it. Uh-oh. Okay, yeah. We're gonna talk about the deep networks with information. So I would have to kind of lead a discussion, but I think it's usually that's when we do have more of like an open discussion in these meetings. So the paper summarizes the findings in the abstract. So some of the kings are that in training a deep network model, are doing compression trainings. The data after some period of time, it's more compressing the input data to find a minimal representation of that. I'm back. I'm on the internet here is kind of so sorry about that. Can you hear me?
We can hear you, Jonathan, but your voice is breaking a lot.
Sorry, but I'm gonna turn off my camera. So if my voice is keeps picking up, and sorry, maybe we'll figure something else out. But hope that this. I'm really sorry about that. I guess the internet in this hotel is really bad. Let's try it one more time. Oh, I can barely hear you.
Your voice is good, Jonathan. Let's try it again.
Okay, trying again. Yeah. So the when you train a deep neural network, the information, the compression of the inputs approaches the theoretical boundary that is the information bottleneck. Another key summary finding of this paper is that the more hidden layers that you have in your neural network, that reduces the training time. And then after some period of time, those hidden layers will converge to a specific set of weights. This is just a brief outline of the paper. This is this is just all the sections of the paper, and I'll go through each one of these. So we'll talk about a little bit of background of information theory of deep learning, and then talk about the numerical experiments that they did, which are all kind of toy models, and then some of the results that show the way that the network converges to that information bottleneck theoretical boundary, and then some information on the two different phases of the learning process. One is drift, and then one is diffusion. This is a little background on the deep neural network architecture that they use. They use a fully connected feed-forward network, and one of the key things is that they are considering all of the layers of the network as one kind of lumped independent variable when they talk about some of the processing, but then they split up each one of these layers to try to quantify the amount of information the layers have with both targets and the input data. So a major theme of this paper is this information bottleneck. So there's a ratio of the mutual information between the true targets and the predicted targets, and then the inputs and the true targets. And with that ratio, there's a theoretical boundary of how much mutual information there is in the input data. So they're actually in the model. So when the input data goes into the first layer of the network, it gets processed, and at each subsequent layer, all of the layers of the input, or all of the layers of the network, compress the information from the input data, and that's represented here by U. So there's a theoretical boundary of how much information there is of the model, which is represented by U, on both the input data and the true target data. So what this is saying is that you can compress the input data through the model U into a minimally representative set of weights that are then used to make the prediction of Y. So this is the information bottleneck. The authors talk about the fact that they train 50 different models for their experiments, and each one of those 50 models has a bunch of different set of weights and biases. And so they make this point that the interpretation of a single neuron in the network is practically meaningless. I think an important point here is that this is in the context of each neuron's weight in the family of trained models. It's not, I don't think it's meaningless in the perspective of what that weight is with the other individual neurons in the model. So for instance, when we've talked about some of the results from, for instance, Lee's paper from 2022, finding the hydrological conceptualizations within an LSTM, there is, I think there is relevance and meaning to the weights themselves, as if you train a model to like represent a hydrologic process, each one of those neurons might represent the hydrological regime, or at least there's evidence that that might be the case. But that's on any individual model, and then that is with respect to the other neurons in the individual models. So when this paper talks about the weights being meaningless, they're talking about it in terms of they train 50 models, and the neurons that span those 50 different models have different weights. So there's many different sets of weights that can reproduce a fairly equivalent model performance. So they use stochastic gradient descent in their training process, and they talk about that quite a bit. And they make the claim that there's two phases of stochastic gradient descent. The first phase fits the labels, so that's the actual training. And then at some point that saturates, and then it moves to a second phase, which is compressing the input to maximize the conditional entropy with the target data. And in doing so, when you compress the model, the compression of the model, then it starts to lose information with the input data themselves. And then we'll see some results that show that the information in the model converges to the theoretical boundary from the information bottleneck. And a couple of another result is that when you add more hidden layers to the model, they claim that the main improvement is computational, not necessarily predictive accuracy. So if you add more layers to your model, you're likely to approach a reasonable solution faster, but not necessarily get to a better solution. Although I think there's some context with this result that is specific to this experiment. Because their computational setup is fairly simple. Couple of bits that they mention on information theory in deep neural networks is that they kind of put a deep neural network in the perspective of a Markov chain, where you start with your desired output y, and then you have your input data x, and then you have a representative set of your input data t, and that representative set has more information about y but less information about x. So you have this Markov chain which moves through these different different aspects of your model. So that from your target data, your input data, then your model itself, and then your predictions. So that they do mention it a couple times. They treat all the hidden layers as a single random variable t, but then again they start to break up the individual layers and try to quantify the mutual information between those individual layers with the input and target data. They point out that invertibility is an important aspect of neural networks. I think there's a silent next, so I'll leave that one out. So this is just some background on mutual information in deep learning itself. So here they're just defining the mutual information between two sets with the KL divergence, and then with entropy itself. So this is the metric that they're using to generate their results. And the reason they're using information as their metric is because of two important properties that are required for analyzing the neural networks. And one is invariance to invertible transformations. So the mutual information between two sets x and y is going to be equal if you invert either or both of those sets x and y with any invertible function. So basically meaning that you can reorder or transform these data any way you want, and still get the value of information between the two sets. Then another key aspect to this mutual information as a metric is the data processing inequality, where if you have inputs X and your target Y, the mutual information between your inputs X and your target Y is greater or equal to the mutual information between those inputs and your model Z here. Although I can't remember why they used Z in this case instead of T. But basically, this is just saying that the processing of your that your model does cannot add information to the system. Right? You can't add information about your target labels. Can everyone still hear me? The screen kind of flickered for a minute.
Yes, works very nice now.
Okay, cool, thanks. So part of their analysis is to describe the progression of information through the network, and that includes the network T on the target data Y, or the layers of the network T1 through TK, which is 7 in this case. So they have 7 layers in their network. So they extend that data processing inequality out to each layer of the network. And so they have each layer of the network on the input data and the target data. So here they're just extending the data processing inequality out to include each layer of the network. So I think there's just one more slide of background on the information perspective of their experiment, which this expresses T as the minimally sufficient statistics on the input data X. So one of the points of the information bottleneck and one of the points of attempting to compress the input data is that there's some sufficient statistics to represent the input data themselves. And these can be solved for a normal distribution, or actually any distribution that is in an exponential family. You can solve for the sufficient statistics. But in the real world data, with real world data, the neural network will try to compress those inputs into something that represents the sufficient statistics. And if you take that to the limit, you will get the minimally sufficient statistics, which is the information bottleneck, where you can't process the inputs any further to maintain the information on Y that you're predicting. And then as a way to test the hypothesis that the layers are approaching the theoretical information bottleneck, they are solving for a Lagrange multiplier beta that captures the level of relevant information from the network T. And then, and then they describe the role of noise in the network, where if there's no noise in the network, then the mutual information is insensitive to the complexity of the deep neural network. So there's not as much processing that can happen if you don't have some noise on your data. And here they describe some of the ways that they're going to visualize the information using the information plane, which includes all the different layers in their network. Okay, so let's get into the experimental setup, where They're using a feed-forward neural network with 7 layers. The task of the neural network is, I guess, kind of vague in my understanding, but they're taking some input data that is binary, and they have some decision rules, and they're trying to map those input data onto points on a 2D sphere. So their network takes input data with size 12, and then it, through 7 layers, processes it to a two-dimensional representation of the target. So the layers go from 12 dimensions down to 2. And I think it's important to point out that they strictly reduce in size. So each layer of the network reduces in size from 12 to 2. So this means that the network can only compress those data. So as you go from the input layer, which is 12 dimensions, down to 10, 7, 5, 4, 3, and 2, you're compressing that those data. And then since this is a very simple problem that they're trying to solve with the neural network, the mutual information is very close to 1 that they're dealing with. So that's the mutual information of the input data X on and Y that is very close to 1. So they have the potential to maintain almost all of the information through the network. So this is a way that they can test the network, the processing of the network itself. So how do they calculate the mutual information? They layer the neurons, or each layer of the network, they bin those neurons from -1 to 1, and so they can use a histogram to calculate the mutual information with they use 30 bins in their calculation. And then they have 50 random initializations. So they calculate the mutual information for each of the 50 random initializations, and then also for each of the layers themselves. So here's the first result that they have, which these 3 plots show 3 different snapshots of the model training. So these are 3 different snapshots of epochs through the model training, where I think it's the initial weights, and then after 400 epochs and 9,000 epochs. So what's going on here is that the information at each layer, let me back up. Each one of these points represents a single layer from a single model, a single one of those 50 different random initializations. So any point here is color-coded according to the layer, but then within the color-coded clusters, you have 50 different random initializations. So each one of these points represents a single layer from a single model. And presumably the input layers here are in orange that have the least amount of information between the model itself and the input data. And then to the top right of each one of these, you have the output layer, presumably, which has the most amount of information between both the model T on X, the input data, and on Y, the target. And then as you progress through training,
Jonathan,
yes.
might it be the other way around, that the first layers still know most about the input and the last layers know most about the output?
Let me think for a second. Yeah, that makes sense. That makes more sense. I'm wondering though how the input layer knows so much about the output at this point. So that's interesting. Yeah, that's a good point. I don't think it actually says what the color coding of those dots are though. That would be good to know. Did anybody see that? But I believe you that that would be the case.
So yeah, I still don't get it, because let's say the green dots in the upper right corner of the first left plot, they have high mutual information of the model and the input, but at the same time, they do have high mutual information between the model and the output as well. So that's also not in line with what I first said. So I'm a little lost here.
Yeah, I'm looking at the paper right now. I don't see anything that indicates how they're color coded. So that's an interesting point. They include a video of this. This might help us understand actually. So what's happening in this video is that the model trains, these are gaining information between the model and the targets Y. They also gain information initially in the beginning on the inputs. So they go from the bottom left to the top right, but then they start compressing the information. And then that compression allows the model to get more mutual information between each layer and the target. But there is at least a couple, there's one layer that is always at near 1 for the model and the target. And I would assume that's the output layer. Because after the first epoch, I guess I would intuitively think that the output layer has more mutual information on the target than the inputs.
I have a question, I think.
Okay.
So in watching this video then, does that mean so the optimal model where we have the highest mutual information between the model and the output isn't necessarily the one with the highest mutual information between the input and the model? Right. So I guess I'm just watching.
It's actually, yeah.
Go ahead.
It's the optimal has the lowest information of the input because it's getting rid of. So the input data only has some amount of information that's useful for the target, the mutual information between X and Y. Most of the information that's in X itself is irrelevant. Well, not most, I don't know, it depends on the system. But hypothetically, there's at least some information that's in X that's irrelevant to Y. And so the model is compressing that information out of the system.
Yes, that makes perfect sense. Okay. Thank you.
So that's essentially what these figures in this plot is showing. So that's one of the results. And the next plot shows not a snapshot, but kind of the information plane that has all of that in it. So it shows this is for those same epochs, or oh no, this is subsetting the training data. And the epochs are shown on the color coding here, and then this is with subsets of the training data. So if you just look at the furthest right plot, it shows that as the epochs progress, just like what we saw with those dots, you can see that there's a plane of how that takes place. So it starts with at least one layer. I don't either that presumably the input or output layer, but maybe the input layer has little information with the targets, the true targets in the beginning, and then as you train it, it gains information with those targets at the expense of information with the inputs. So the ordering of that, I don't know. I put these in order of figure number, but actually this is probably would have been a better next figure to show. This shows the two phases of that. So in one phase you have, so they consider the phases by how much change takes place with respect to the magnitude of the means and the magnitude of standard deviations of the model weights themselves. So at some point through the model training, there's obviously an inflection point, and that inflection point probably starts the phase of learning to fit the training data, and then it starts compressing the input data. So this happens near 100 epochs here, and if we look back at this figure, I guess we can't tell from the color coding, but I was gonna try to make a claim that this inflection point here in the information plane, where the mutual information starts increases between the input data, and then it starts to decrease with the input data, that this is the beginning of that compression phase rather than the learning phase. And so that's what I think is happening here in this inflection point. But then they refer to it as I think the phase change starts, they call it the diffusion phase, once the standard deviation values, the magnitude of the standard deviations of the model weights crosses the magnitude of the weight means themselves. So whether it happens between like closer to 100 or closer to 1,000, this is the period of the phase shift basically between 100 and 1,000, where once the magnitude of the standard deviations exceeds the magnitude of the means, then the model is more working towards compressing the input data rather than fitting the training data. And so they liken this to a diffusion process, and they can model that diffusion process. And with if you model the diffusion process, then you can get an estimate of the compression through the epochs. And so they're using, I think they talk about a couple different ways to model the diffusion, but generally, if you can estimate that diffusion, then you can estimate the compression.
Jonathan, a short question. Is it correct that for optimization, they directly optimize as the objective function for the information bottleneck equation, basically? Or do they optimize for some standard, say, root mean square error, and then they just evaluate that through the information bottleneck?
They're not evaluating anything through the loss function. And actually, I don't really remember them discussing the loss itself in a paper.
Yeah, because I was wondering if they would be optimizing for some root mean square error or so. It would be interesting to look at the loss function and see whether, you basically saturate in learning whenever these phase changes occur in the information analysis.
Yeah. Yeah, I don't, that's a good point. I don't remember them including anything that would give that indication. Like they don't include like a plot of the loss function, which is usually what, you know, is reported and what is the focus of training. But in this case, I don't remember seeing that at all.
Yeah, that's why I was not sure whether they optimize
never...
for the information bottleneck quantity, like, you know, minimizing mutual information with of the model with the input and maximizing mutual information of the model with the output, whether this is the objective function or whether it's just a diagnostic they run as they optimize for some other typical objective function.
I don't see the word objective in the paper itself, and I don't, let's see. Yeah, I'm not sure what they're optimizing for. They're using a cross entropy loss function. So that would be, I think, more in terms of trying to optimize for the mutual information itself rather than a root mean squared error.
In regards to the paper, I'm still a little bit confused about the experimental setup that they use, but I did saw a similar implementation of this paper in papers with code, and as I remember, they don't specifically optimize for the information bottleneck, but they do use a specific loss function that in the code, I'm looking at the code right now, and it says EMA loss. So I don't think it's specifically the bottleneck or related to the bottleneck. I would think it's more related to some kind of MSE. But yeah, in regards to the experimental setup, I'm still a little bit lost. Still, I like the concept of the paper.
Yeah, I think it would probably be a good idea to reproduce this and try to include the loss in this information plane landscape somehow. You know, you can reproduce this plot with an instead of color coding it by epochs, you can choose one epoch and color code it by the loss itself, and that might be informative as to if, for instance, the inflection point happens when there's no more progress towards decreasing the loss function. Here's I think this is the last result I'll show here, but this they try some sensitivity to the number of layers themselves. So they have a couple different. They tried it with between 1 and 6 layers, and so with only one layer, what happens is you don't always converge to the highest amount of mutual information. So within presumably all the different random initializations, you have some random initializations that have higher mutual information between the target data themselves. But as you increase the number of layers in your network, then you're consistently getting up to the maximum amount of mutual information. And then now I'm just seeing that the y-axis here only goes to 0.7 in this plot, which I didn't catch before. And then this plot shows that when they calculate the beta, the Lagrange multiplier on for the layers, that Lagrange multiplier approaches the information bottleneck front. And so this is their evidence that their model is sufficiently compressing the input data themselves. Oh yeah, here's the other plot that I thought that previous plot slide was, but this is showing another sensitivity test where they specifically subset the training data. So they have whatever full set of training data they have. They run the experiment with just 4%, and then they increase that up to 84%. And that shows that the more training data you have, let's see, the first layers, I said first here, but I think we don't know if that's true. That leaves some layers with let's see here. Oh yeah, if you only have some small subset of the training data, then that does not give the network enough information, enough data to find the compressed representation of it, the sufficiently compressed representation of it. So it remains with low mutual information between the network itself and the label data. So that's they do have this one more plot where they just changed the network. So they, in the beginning of the paper, they actually say that they're only going to use one architecture, but then they throw in this second architecture at the end, and they say it has the same results, but then at the end of the training, it drops off. The magnitude of the standard deviations and the means drop off at the end, and they don't really explain this. I don't know if anyone else saw an explanation of this, but they kind of left that out. So they just threw this last result in at the end and didn't really go over it very well. So I didn't really even want to talk about it. So that's my outline of the paper. So I think it'd be good to have more of an open discussion about it.
Yeah, thank you, Jonathan. If anybody has any question, they can ask.
So Jonathan, this is Jasper. So just first a general question. So when is a neural network a deep neural network?
Oh yeah, that would be when it has more hidden, some number of hidden layers. So in where was this plot? This only has one hidden layer, so I would assume you wouldn't call this a deep network, but I think with two hidden layers, you would start to call that a deep network. Although I don't know off the top of my head if there's any specific number of hidden layers that are required to call it that. I think MASH, you probably would know that.
Yeah, something.
Do you still hear MASH?
Multiple fully connected layers. That would be deep learning network instead of just a feed-forward network. So yeah, so multiple fully connected hidden layers. That would be something.
And what is multiple?
I would say like one or more than one. I would say.
So with one hidden layer, then that would be a deep network, because there's an intermediate layer between the input and the output.
Correct. Yeah, and like they are all fully connected. They're all fully connected. So that's also called a dense layer, right?
Yeah. But the word deep refers to the number of layers, not the connections between them.
Yeah, correct. Yep.
As far as I know.
And so this mutual information, equation 1 and 2 in the paper, I don't, I'm not familiar with this specific form that they use with the bivariate distribution. There is no reference there either, but I don't know, maybe you guys are familiar. Oh yeah, here you, okay, good. So I see that you divide by the distributions of X and Y, they're marginals, they're PDFs, at the right-hand side in equation 1. So I'm not familiar with this formulation. Anyway, I don't see a reference either. Is this a common formulation for bivariate data, X and Y?
I've seen this quite often. So it seems like a pretty common formulation from my perspective.
Okay. Yeah. Okay. And yeah, the question always, are the distributions normalized or not? So Px given Y in equation 2. So Px given Y, is that a normalized distribution or is it non-normalized, unnormalized? Because you have Px comma Y and Px given Y, and one of them is unnormalized and the other one is normalized, meaning integrates to 1.
Right. So are you asking in general or with
I mean, I can go back
the data
to my,
that they used in the paper?
Yeah, so because, you know, the next step is to implement, right? Implement it, and that's why these questions become important. If that's a normalized distribution, meaning it integrates to 1, because Px comma Y, I think that is equal to Px given Y divided by Py, something like that. So I need to look that up, but anyway, maybe you're familiar with it. I think Px comma Y is not normalized. So there's no normalization taking place there. It doesn't integrate to 1, and Px given Y, I think, is normalized. But there's no explanation in the paper. It's just assumed that that is, yeah, understood. Joint distribution. Yeah, okay. Anyway.
Yeah, so I would assume that P of X comma Y is the joint probability, so it should normalize or sum up to 1 over the entire joint distribution of X and Y, where P of X only and P of Y only should normalize because they're the marginal distributions over X only or Y only should normalize over all these cases of X and Y.
And Px given Y?
That should also normalize to 1 because that's a conditional distribution of X given a particular Y. So that should also sum up to 1.
Okay, so you see here that I come from a Bayesian background where Px comma Y is not necessarily a normalized distribution. So anyway, it's a notation thing. That's why explanation of notation is so important to understand. Okay, thank you, Owa.
Actually, I'm also most familiar with that formulation saying the mutual information of X and Y is, and then the end of these two row equations saying it's the entropy of X minus the conditional entropy of X given Y. That's also what I'm most familiar with, not the intermediate formulations.
Exactly. Yes. Yeah, so I'm sorry. So yeah, what I really miss in this paper, to be honest, is an explanation of the target variable Like a little bit like this goes back to the discussion about the loss function.
Yeah, I definitely
and like a
was
little bit of a
trying to figure
time
that out
series
too.
that they're trying to describe, right? And then like this is so general, and also some of these conclusions seem so general stated. And I question whether about the generality of some of their findings. It's a very interesting paper, really, really interesting. But some statements, I don't know, they seem to be so general. Yeah.
I definitely picked up on that as well when I was trying to like write a summary of the experimental setup here. When so this is their description. They have 12 binary inputs that represent 12 uniformly distributed points on a 2D sphere. So are they just trying to predict the coordinates on the sphere, I guess? So like that seems like a pretty easy thing to do, which is why the information is always close to 1. So it's not, I definitely also question the generality of this, because this is never going to happen with any real data.
Mm-hmm.
And yes. I think most importantly, when you look at these inflection points here, I don't think that there's any way to know. I mean, we can run the experiment with real data, which would be, I think, really good. But yeah, I have a hard time figuring out how, in my experience training neural network models, I don't see this. So I haven't looked at these specific types of plots, but I generally don't see like these big inflection points on with these metrics. So
I agree with you. I agree with you. I think it was really well stated about close to 1 bit, because we're never in hydrology or any applied field where you try to describe a complex system. It's never going to be the case. And the question is how that's going to affect your conclusions. That you always have. You always have insufficient, your inputs will never contain all the information, right? There's always missing information. So, yeah. So that's why it's interesting to redo what they done for an hydrologic case study, just some time series of discharge or whatever. So.
Yeah, I think that's a great idea. I'd be interested to give that a shot.
But then you also probably have the issue that you have those gates, right? That you need to provide information from system past, because it's not an instantaneous system, a hydrologic system. Whereas this is an instantaneous system. Whereas an hydrologic system has state variables. So that's also really going to affect the analysis.
Yeah, I do have the data set that I'm working now. We train from the hydrologic state variables instantaneously onto an output at every point in time. So the data that I work with mostly right now it has the history in the hydrologic state variable, but that's what goes into the network itself.
Okay.
So
okay.
That could work.
Yes.
It's a very complicated system, so it'd be hard to boil it down to a representation that we can get these results. But I think I can, just for the sake of applying it to a real world scenario, I can select a couple of very simple examples and maybe try to reproduce it.
Because personally, for me, always reading a paper is one thing, but once you really start to code, that's when really the questions come to the surface, right? The deeper understanding of exactly what's going on. And but anyway, I understood from one person saying that there is a code with this paper or so that authors provided. So maybe that helps.
I found an implementation by a different set of people. I can post the link in the chat.
Okay. So is this paper, I didn't check, I printed it, but is it cited a lot or not?
It's pretty well cited, yeah.
Okay, good.
Jonathan, I have a general question of understanding. So the information bottleneck does have nothing to do with compression, right? In terms of expressing what's needed in fewer bits. Like if I take a set of input data, let's say this is a single predictor neural network and it predicts a single output, then whatever, if you have 1,000 data pairs, then it's 1,000 input values to map to 1,000 output values. Now, if I replace these 1,000 input values by all the states that my neural network has, yeah, because that should then also be predictive of the output. Then I've inflated, say, my 1,000 input points to, say, 1,000,000 neural network states that I'll have to keep. Of course, if I do the mutual information of this 1,000,000 node values to the output, it's still a high mutual information, and it may have decorrelated as much as possible from the single output value or from the 1,000, input values. So the information bottleneck just strips all information in X that's not really relevant for Y, but may store it on many more data. So is this correct? Would you agree to this? But it's not compression necessarily, data compression.
So I agree that it's not compression that we have fewer, we need fewer bits of information to represent it. But I guess when I was saying compression, I was thinking of it like I guess I should have been saying extraction rather than compression, because I wasn't trying to explain compression in terms of reducing the amount of bits required to represent it, but extracting only the information and that is necessary to represent it. How you extract it, though, is a different
I mean, that's
a different question.
I was until today also intuitively under the impression that if you feed the data through an information bottleneck, you will also store what's necessary on less bits. But that's so it just occurred to me now when you talked that this might not be necessarily the case.
Yeah, that's a good question. So in their case, they do go from only down in their dimensions. So it is in less bits through the network. So the last layer has fewer less bits representing. But if this wasn't, if this was just 12 all the way through, then down to 2, we would have the same number of bits, but I think we would have the same amount of unused bits. So whatever irrelevant information from the input data is in the input data there would still be irrelevant information in layer n-1 if the layers weren't getting smaller. But it would probably
but you need this
different
inflation first to strip the irrelevant information away, I guess.
Why? Why? I don't. Oh, okay, I don't think so, because they don't do any inflation in the layer size.
No, I mean inflation in terms of if you only have a single input value and you feed it through a network, you map it on a higher dimensional data plane or a data cube, because a single value is then represented through all the values that are being touched and changed in the network. And then you may go down to a single output value, but I guess you needed this internal mapping to a higher dimensional sphere to be able to rearrange the data and strip everything off that's not necessary and rearrange such that you can predict the output with its value.
I'm not sure I agree, but I can't really say why. So in this situation, the input is the same. So I think, if you look at the individual layers themselves, let's see. Okay, I was going to try and make a point, but it's not true here. So I guess it's interesting that at some point in the training, the mutual information with the target data is very low for one layer, but not another layer. So I'm not really sure how to, I don't think I have an answer for that question.
Yeah, I guess if we forget about the information perspective for a minute, what I got from Hoshin mainly is that what happens in a network is you need this internal large number of variables or states such that you can rearrange whatever is in the input to the values that are your output. And this rearranging by your weights and biases and nonlinear transforms just requires a certain, playground to do that, and that's the size of your model. But so that means there's actually first an inflation of data. If you only feed in a single input value, it creates 500,000 model internal values until you're down to a single output value again. So that's where the data inflation comes in, and later a compression down to 1 again. But the data are all there. And if we then take the information perspective, we are not compressing the data, but what we do is we strip the irrelevant information from X and we keep what's relevant for Y. And I was falsely always under the impression that the information bottleneck also always means a data compression, but that's definitely not the case.
So I agree about that, because you're not compressing. I agree that it's not always the case that it's a data compression, but I think it can be.
It could, yeah. That's what I was assuming. If you strip irrelevant information from X, you should be able to represent the remaining on lesser bits.
If you know what it is, but if you strip the information from X on an inflated network, then you also have you have to replace it with other non-relevant information.
Yeah, that's an interesting thought. You could, in the information bottleneck, you could replace the irrelevant information in X about Y with random noise, and you still preserve what's relevant about Y, and you just stripped off everything in X that was not useful, but you replaced it with other rubbish, basically. And that's why I was under the impression, hey, you could also then at the same time do data compression, because you only need to preserve the amount of information that's relevant about Y. And this by definition is less variable than the variability of X, because X cannot know more about Y than Y knows about itself.
Right. So I guess what's kind of troubling me is that our lack of really understanding the input and target data here, because it could be the case, and like this kind of goes back to the short discussion on what it actually is that they're representing. It could be the case that it's actually highly likely that you don't need a neural network to do this mapping from these 12 binary inputs to points on a 2D sphere, that there's a simple function that will do this, except for maybe the added noise that they use. So, I mean, if that's the case, I mean, the most compressed you can get is just the function itself. Plus, you only need one more bit for the noise, or some minimal amount of information to represent the noise. So it's hard for me to think about this, because in this toy example, you don't really need you can simply just compress it, I guess, with a toy example, because the network can learn that analytical function. But in a real world system, there's no analytical function for it to learn. So it's tough to really think about that. I have to get going. So I'm gonna hop off. Thanks for your attention. I assume you'll continue. But yeah, thank you all. I'll
Thanks,
talk to you
Jonathan.
later.
Thank you, Jonathan. Yeah.
Thank you. Nice seeing you again.
Yeah, you too.
See you all in the next meeting.
Bye.
Bye.
Bye-bye. Thanks for having me.
Thank you. Bye-bye.